Hi everyone. In this video, we are going to um, cover two examples for hydraulic jump. Uh, so, in both examples, we are going to see how we can use the formulas that we derived before in order to apply and solve some practical examples in open channel flow um, context. So if you remember, we derived some formula for the ratio of the depths before and after the jump, which was a function of the upstream Froude number. We also derived a formula for the head loss based on energy equation that occurs in within the hydraulic jump because of the violent turbulent motions. And so these equations were derived from three principal equations, three governing equations, which were conservation of mass, momentum equation in the x direction, and also energy equation. So we use those three equations to drive two relations for hydraulic jumps. And in these two examples, we're going to see how we can apply those relations. Okay. So let's look at the first problem. In the first problem, you can see that we have a channel like a spillway. These are some common open channel flows, especially in engineering design. For example, when you are designing dams or like open channels, so you have a spillway here, and then we have some obstacles downstream. These obstacles could be either some built structures, or it could be any like natural obstacles, for instance, like plants or any other things. So assume we have some obstacles here, either natural or built, and then this spillway because of these obstacles, the velocity is gonna decrease a little bit, and we can assume that we have like a subcritical Froude number here because of this decrease, and then here we have high velocity speed flow, which can come from like under a slice gate from like a dam or any other problems, like if you remember slice gates, and also you had it in your lab. So this is coming from there, the incoming fluid, and the incoming velocity is 18 foot per second. The width of the spillway is 100 foot. The depth of the incoming fluid is 0.6 foot. The depth of the fluid after the jump is unknown. Also, the velocity after the hydraulic jump is unknown. And here you can see a jump occurs because a conflict between the upstream and downstream conditions. Okay. So this is the configuration of the problem, and the problem the question asks, determine y2, which is the depth after the jump, Froude number 1, which is the upstream Froude number around here, Froude number 2, which is the Froude number here, the Froude number after the jump, and the power dissipated within the jump. So how much power or energy or power is dissipated, PD, which we showed with PD within this jump. And this is very important, especially for hydraulic engineering applications. Sometimes you want to actually decrease the power of water or the energy of water, like on purpose, because you want to avoid some damage later on. So we want to calculate this power that is dissipated within this jump as well in this problem. Okay, so the first thing we do is we first calculate the upstream Froude number to find whether actually a jump occurs, and also because the problem wanted us to do that. So first calculate upstream Froude number. So Froude number, the definition of the Froude number is V1 over square root of GY1, okay? So these are all the things we know from the problem statement. V1 is 18 foot per second. G in British system is 32.2 foot per second square times Y1, which is also given in the problem, is 0.6 foot. So we take the square root of this and divide it divide 18 by that. So we get the upstream Froude number here, which is 4.1. Okay. So as you can see, the Froude number, the upstream Froude number, 4.1, is greater than 1. So here we have a supercritical flow. And as you know, as you remember, hydraulic jump is possible in this regime. When you have supercritical flow, hydraulic jump is possible, and we showed that when you have a subcritical flow in which what Froude number is smaller than 1, hydraulic jump is not possible because it's not gonna satisfy the thermodynamics law, because the energy loss is gonna be negative. Okay, so this is the only possible, the only way it's possible, which is the upstream Froude number should be supercritical or greater than 1. Okay, the second thing I want to do is I want to calculate Y2. Okay, I want to calculate Y2, and in order to calculate Y2, I use the derived relation that we found for Y2 over Y1 before and after the jump. So after and before the jump. So this was the relationship that we found for based on continuity and momentum equation for hydraulic jump. So Y2, which is the depth of the fluid after the jump, over Y1, the depth of the fluid before the jump, equals to 1/2 minus 1 plus square root of 1 plus 8 times Froude number, upstream Froude number, which is this one, squared. Okay, so upstream Froude number is given here. We found it here is 4.1. So we just substitute it here in this formula and then calculate this ratio between Y2 and Y1, which is gonna be 532. Okay, so Y2 is 532 times Y1 and larger than Y1. So the depth after the jump, which is Y2, and which is what is the problem, one of the things that the question asks from us is 5.32 times Y1, which is 0.6 foot. So Y2 is going to be 3.19 foot. Okay, so this is the second thing that the question wanted us to find. And then the third thing is Froude number 2. So let's go and see how we can find it. So in order to find Froude number 2, we need to know the velocity, the downstream velocity. So to find the velocity, we use continuity equation between section 1 and section 2. So we set Q1 equals to Q2. And so based on that, we can get V2 times Y2, because B, the width of the channel, is 100 foot, is constant, it's a rectangular channel. And so we get, to this relation where v2 equals to y1 times v1 over y2, and y1 and y1 over y2, we found it here. So y1 is 0.6, y2 is 3.19, and times multiply it by 18 foot per second, which is v1, we are gonna get the velocity, the downstream velocity, which is 3.39 foot per second. Okay, so now that we have the velocity, the downstream velocity, which is smaller, actually should be smaller than v1, which is what we expected, because the downstream should be in a subcritical regime. So now we just set it into the definition of Froude numbers at the downstream. So Froude 2 equals to v2 or a square root of gy2. So v2 is 3.39 foot per second, g is 32.2 foot per second square, times y2, which is 3.19 foot. We take the square root of that and then calculate this Froude number, and this is gonna give us 0.334. And as you see, and as we expected, the Froude number 2, which is the downstream Froude number, is smaller than 1. And this shows that this problem satisfies the hydraulic jump criteria. Okay. And so you see that we go from a high-speed, shallow, like channel to a low speed and deep channel configuration or regime. Okay, so now the last unknown in the problem which we have to find is PD, the power dissipated within the jump. Okay, when you want to find the power, if you remember, it's related to the head loss. So we have to find how much head loss we have here in this hydraulic jump. So we have to use the energy equation. Okay, so the power is, the definition of power is energy per time per unit time. So the power dissipated, or PD, if you remember, it's related to Q, the Q and gamma, the specific gravity through this relation. PD equals to gamma Q times HL. Okay, and for Q is VA, right? And this is A. So this is the area of the channel. So Q is, instead of Q, I just write VA, V1A. And so B, which is the width of the channel, times Y is going to give me the area of the channel. Multiply it by V1 to get the flow rate, and multiply it by gamma, the specific gravity of water, and HL to get the power. Okay, so the only unknown here is HL, so we have to find HL, and everything else we have calculated everything else. Okay, or have it from the problem. So let's calculate HL, the head loss here. So HL, the head loss, is the difference between the energy at the upstream and downstream. How much the energy we had at the upstream and how much we had at the downstream. And the energy is, we can write it as Y1 plus V1 square over 2G. This is kind of potential and kinetic energy, and minus Y2 plus V2 square over 2G. So this is going to be the difference of the energy between section 1 and section 2, and this is going to be the head loss in the system. Okay, so let's calculate that. So instead of Y1 we have 0.6 foot plus v1 square is going to be 18 foot over foot per second squared over 2 times 32.2 foot per second square. Okay, so this is G minus, instead of y2, y2 is 3.19, we found it here, 3.19 foot plus v2 square, v2 is 3.39 foot per second square over 2 32.2 foot per second square. And if you calculate this, you're gonna get 2.26 foot. So we have a head loss of 2.26 foot after this jump. So let's put this and substitute this here, put this here and see what we are gonna get, how much power actually has dissipated in this hydraulic jump. So PD equals to gamma times by1 v1 HL. So equals to the gamma water, the specific gravity of water is 62.4 pound per foot cube times B is given is 100 foot, then multiplied by Y1, which is 0.6 foot, multiplied by V1, which is 18 foot per second, times HL we found it here, 2.26 foot, and we are going to get 1.52 times 10 to the 5 foot pound per second. Okay. And then I want to convert it to horsepower. So horsepower is the conversion rate for is 550. So I just converted to horsepower, 1.52 times 10 to the 5 foot per, pound per second over 550 foot pound per second over horsepower. So this is a conversion rate. It's gonna give me 277 horsepower. Okay, so 277 horsepower is lost during and dissipated during over this hydraulic jump. Okay, so this was the first example I wanted to solve for you. Let's go to the second example of hydraulic jump. Okay, for the second example, it's kind of similar to the previous one, but now in SI unit. So we have a rectangular channel. The width of the channel is given 6 meters, which discharges 1,200 liters per second into a 6 meter wide apron with a velocity of 6 meters per second. So the question one asks us, what is the height of the jump? First, and second, what is the power absorbed in the jump? Okay. So similar to the previous example, the first thing I want to find is what is the for this problem. First I want to find what is y1, because I don't know what is y1, what is the depth of the fluid before the jump. Okay, so let's see. Here we have these are the givens. So we know the depth width of the channel. We know the Q, the flow rate, which is 1,200 liter per second, which is going to be 1.2 meter cube per second, because every 1 meter cube, if if you don't remember, 1 meter cube is 1000 liter. Okay, and V equals to 6 meter per second. So these are the givens in the problem. So I want to find first Y1 and then Froude number and then use that relation. Okay, so Y1 I can find based on the givens. Q is A times V, right? So and it equals to 1.2 meter cube per second, which equals to BY1, which is A, times V. And if you calculate this, you are going to get Y1 is going to be 1.2 over B. B is 6 meter, and V is also 6 meter per second. So I'm going to get 0.033 meter. So the Y1, the upstream depth of the channel is 0.033 meter. So now that I had this, let's calculate the upstream Froude number. So the upstream Froude number is going to be V over square root of GY1. So it's going to be 6 meter per second over square root of 9.81, which is G, times 0.033 meter, Y1. And this is going to give me 10.55, which is the upstream Froude number, and is again greater than 1, which shows that a hydraulic jump is possible here. Okay, so now based on the relation we derived for hydraulic jump, we want to calculate the Y2 to be able to find the height of the jump. Okay, so Y2 or Y1 is 1/2 or times minus 1 plus square root of 1 plus 8 times Froude number 1 squared. So Froude number 1 is the upstream Froude number which we found here. So you just substitute here 10.55, then calculate this expression, and you will get the ratio between Y2 and Y1 is 14.4. So Y2 is going to be 14.4 times Y1, which is 0.033 meter. So Y2 is going to be 476 meter. 476 meter is going to be the downstream depths of the flow. And what is the height of the jump? The height of the jump is going to be Y2 minus Y1. So Y2 minus Y1 is going to be 0.44 meter. Okay, so you just subtract 0.33 from 0.476, and this is going to be the height of the jump, about 0.44 meter. Okay. So this is the first part of the problem, and for the second part of the problem, I want to find what is the power absorbed in the jump. So in order to find what is the power that is absorbed in the jump, I need to know what is the head loss. Okay, so I need to know what is the head loss in the system, which is shown here. So in order to find the head loss, I need to know the velocity, downstream velocity, so I can find it through continuity equation or mass conservation. So V2 equals to, this is coming from continuity equation, V2 equals to V1 times Y1 over Y2. So V1 I know is 6 meter per second. Y1 over Y2 is going to be 1 over 14.4. So I'm going to get V2 is going to be 0.42 meter per second. And now having this V2, I can find the head loss in the system, which is the difference between the energy level at section before the jump and after the jump. So before the jump, the energy, this is like the potential and kinetic energy, is y1 plus v1 square over 2g minus y2 plus v2 square over 2g. And so if you calculate this, put all the numbers, we have v2 here from here. We have y2 here, and we have y1 and v1 given in the problem. It's going to give us a 1.384 meter head loss. And using the formula for the power, we can get the power absorbed in the jump, which is rho g or gamma q times HL. So I have the rho of water is 1000, g is 9.81, q I have it here 1.2 meter cube per second, and HL is from here 1.384 meter. And if you plug all these numbers here, you're gonna get this much power that is absorbed in the jump. So 16.3 kilowatt power is absorbed in this jump. Okay, so this was the second example of hydraulic jump. And now I want to talk about the configuration of hydraulic jumps and the classification of hydraulic jumps. So depending on the upstream Froude number, the hydraulic jumps can have different shapes and different characteristics. So here we have shown their behavior. So for flows that are barely supercritical, that is, Froude number is not is greater than 1, but is like not much greater than 1. The jump is more like a standing wave, is without a nearly step change in the depth, right? So we don't have that deep or very steep changes in the depths of the fluid. Even the Froude number is greater than 1, but is not much greater than 1. It's barely supercritical. Okay, so let's look at different conditions that can happen. Okay, so if your upstream Froude number here is smaller than 1, jump is impossible. So y2 over y1, if you don't have any head loss, you can assume you have negligible head loss, is going to be always 1. Okay, so jump is impossible. If your Froude number is between 1 and 1.7, you will have a standing wave or jump that's something like this, and your y2 over y1 is going to be between 1 and 2. If your Froude number 1 is between 1.7 and 2.5, you will have a weak jump. The figure is shown here. If your Froude number, upstream Froude number, is between 2.5 and 4.5, you will have an oscillating jump, which is shown here. If your Froude number is upstream Froude number is between 4.5 and 9, you will have a stable, well-balanced, steady jump, and is insensitive to the downstream conditions, something like this. And then for Froude number 1 greater than 9, you will have rough and somewhat intermittent strong jump. So these are the strong jumps that we usually see in nature. So, and then the y2 over y1 value is going to be greater than 12. So 12 times difference in the height of the channel is going to occur. So this is the classification of hydraulic jumps. So based on the upstream Froude number, they can have different shapes and different configurations. And in the next session, we are going to talk about some other hydraulic parameters or shapes. For instance, slide skates, and how we can sharp crested weirs and slide skates, and how we can calculate the flow rates and some other important characteristics, fluid characteristics in that type of hydraulic structures. Thank you very much, everyone.